the next session that is again that will be taken by Professor Vijay Janyani sir. And this session is on gigabit passive optical networks. So now, sir, this session is over to you.
Let me share my slide.
Yes.
The share option is disabled.
भाटी जी, please check the issue. सर को होस्ट बनाओ होस्ट. Yes, now check sir.
Still the same. Yeah, now it is active.
Okay sir.
Yeah, is it visible?
Yes sir, it is opening basically. It is taking some time.
Yeah, when it is ready, just let me know. If it is
Yeah.
visible.
Yes sir. Now it is visible.
Okay.
Yeah.
Okay, so let's start this presentation. Now, in the morning lecture, I basically told you an overview of optical communication, various devices, amplifiers, and optical fibers. Now, this lecture is particularly focused on optical networks, and that too gigabit passive optical network. So, before we move on to the GPON or gigabit passive optical network, it is worthwhile to understand what is the difference, what is actually a network. So if you see this slide, it tells you that there can either be a point-to-point connection or a multi-point connection. The point-to-point connection is what usually we see in optical communication. You have a transmitter and you have a receiver and then you have a link. So this is nothing but a point-to-point. You call it as P2P. Now, when you have a number of nodes or number of transmitter receivers connected together and which they can share data as per the requirement, there is not necessarily a direct connection between this server and maybe this server. They may be connected through some other bus or some other link. So basically, that you call it as a network. So here you see this is a point-to-point link, location A to location Z. Here it is a point to multi-point. Now this is the transmitter and it is transmitting to multiple points. So it is called P2MP, point to multi-point. Because the network that we'll study today, GPON, it is actually this type of network. And then you may have many other configurations. You may have a ring architecture, you may have a star architecture like this, or you may have a combination of this. This is a ring and star. So basically a network is something which have a number of nodes connected to each other in a complex fashion and then they can share the information. So if you see the network topology, basically you can either talk of physical topology or the logical topology. So physical topology means how actually the cable is going from one point to other point, in what fashion it is connected. So that is actually the physical topology, whereas logical topology maybe it's not the same. It affects how the individual fibers or circuit act without regard to pathway or fault tolerance. Say you may temporarily have a connection between two computers. In that case, they are logically directly connected, but they may not be physically directly connected because they may be connected through some routers or something. So this is how the evolution of optical networking particularly it has taken place. So as I mentioned earlier in the morning, that the point-to-point fiber transmission, of course, was the first major, you can say, breakthrough in optical communication. You had a point-to-point link from one fixed point to the other point. Then there was dense wavelength division multiplexing, and then then there was DWDM, and combined with optical add drop multiplexers. You call them as OADMs, that is optical add drop multiplexers, and reconfigurable ROADMs are also available nowadays. So you see that now from a point-to-point link, we are moving towards a network scenario where you have switches and multiplexers and all that built in. These are optical cross connects, OXCs, because when you talk of a network, you have a network and then you have to switch from, let us say, one computer to other computer, or from this transmitter to this receiver. So all these are necessarily required: optical add drop multiplexers, cross connects. So basically this is moving towards the optical network. And as I mentioned, all optical networks is still far reality, but maybe in future we may see this all optical networks. So conventional, what is the difference between conventional electronic or your Ethernet or optical networks? In most existing networks, optical technology is used to transport signals only. I mean, from one point to other point, the signal is being transmitted through the optical fiber. But mainly the main processing which is taking place, the signal processing, that is actually in the electrical domain. So it's not optical. So this OEO conversion is always there. You have to convert from optical to electrical and then again electrical to optical. So these are the scenario of today's network. Optical is there, this link is optical, but these nodes may or may not be optical. So SDH and SONET, these are optical networks which fall under this category. And so moving towards all optical networks where transport and processing both are optical. If everything is optical, then you call them truly all optical networks. And that will give you a real high speed. But as I said, it is still far away. Now, you can divide or classify these networks into various categories. And there are multiple ways of categorizing them. The first method may be based on electrical or optical, which I just mentioned. You can have an all optical network or a OEO network, optical, electrical, optical network. So this is one possible, you can say, classification. Based on service area, and I mean, what is the area covered by the service of that network? You may have long haul, metropolitan, or access networks. Long haul networks means if you see the Earth, I mean the globe, the map of world map, maybe let us say you have US here and then Europe here and then India here. It's not to scale, so don't mind if I am not drawing it perfectly. So India here. So I mean, what I mean to say is long haul networks are these networks which carry huge amount of data. Undersea cables are actually there, optical cables, which carry huge amount of data from here or from one continent to other continent. Those are called long haul networks. They span hundreds or thousands of kilometers. Metropolitan are those networks which are slightly on a smaller scale, maybe one network which is covering Jaipur or maybe another city, Delhi. So those networks you call as metropolitan. And then access networks. These are the access networks which are directly accessible to the user, and user is directly connected to those access networks. So as far as the reach is concerned, these are the shortest reach, and then this is actually GPON, which we'll be discussing today. Similarly, you can have MAN, LAN, WAN, and MAN. Depending on what protocol you are using, you can have SONET, you can have SDH, Ethernet, ATM, IP, or different networks. Number of wavelengths, single wavelength. I mean, if you have a network connected like this, but only a single wavelength is there, then you can call it as a single wavelength network. But if you have multiple wavelengths, coarse WDM or DWDM, then you can also call that network as a multi-wavelength or WDM network. So this is the diagram which gives you an idea about what various network architectures as far as the reach, the length of the cables are concerned. Long haul networks, as I told you, they cover very big distances. DWDM is the prominent technology or protocol used in those communications. All participants, please mute their mics. So DWDM is used here, and then metro network, as I said, SONET, or you may have SDH. SONET is synchronous optical network. SDH is synchronous digital hierarchy. And then you have the access networks, and this is the customer. So this customer is directly connected to access network, and PON is one example. So how do you actually compare these different networks on various parameters? Core network, long haul, or sometimes also called backbone network. So, and then you have metro or regional, and access or local loop. So actually this core and long haul networks, they are only used by very big networks, Lucent or maybe Siemens or something, which very big companies, I mean, they are handling very big data long distance. Metro, it may be operated by phone companies or big businesses, and access may be small businesses and consumers. The span rate of these may be up to 1000 kilometers. This is 100 kilometers, and this is 10 kilometers approximately. It may be 20 also, as we'll see in the GPON. Bit rate, here it is hundreds of gigabit per second, and in fact now it is 1 TBps, terabits per second. Here the bit rate may be smaller, and then when it reaches, it may be 1 Gbps or maybe 100 Mbps to the user directly. These are the common multiplexing techniques which are used. Fibers, it's mostly single mode fibers used here and here because it's a long distance communication and you use very high data bit rate. So only single mode fiber is the option here because it has less dispersion. Dispersion is less. Whereas on local loop, you normally prefer SMF, but MMF can also be used. And similarly for lasers and receivers, depending on the requirement, we use either lasers, LEDs, or laser diodes. So these are the desirable features of all telecommunication networks and particularly optical networks. It should have high capacity. It should, high capacity means both in terms of bandwidth and the number of users it can service. Full redundancy, fast restoration. If there is any outage, it should be very fast. High availability, because nowadays you know that internet has become so important, as good as electricity, or even electricity or something is not there, then you can manage. But if internet is not there available to you, you are annoyed in very small time. So this high availability is very important feature. 99.999% it should be available. Low latency, high bandwidth, dynamic allocation, and high bandwidth efficiency, various services. You know, nowadays you have, apart from internet and data, it's supporting TV services and voice and landline. All these are supported here, and it should be scalable. That is the very important thing, because today you may find a network is good, But tomorrow you may have to add, let us say, double the number of consumers, then it should be scalable. I will tell you later on why, I mean, how this scalability is important and how it has led to development of new protocols. Okay, now coming on to GPON, and before I jump into GPON, this FTTX term is very, very important, and nowadays very common also. FTTX may not be common, but FTTH is very common nowadays. You must have heard this FTTH. This FTTH is fiber to the home, fiber to the home. And this X, actually, X can be anything. It can be fiber to the home, fiber to the curb, fiber to the building. There are various terminologies. Now, if you look at this diagram carefully, see, this is the central office from where all the data, you can say, is originating for the access network. And this, on the bottom part of the in this diagram, you can see that there are different lines drawn. This blue line represents the optical fiber. Then this white one, it represents the gray one, in fact, it represents copper, which is normal copper, which you used to use before fiber came to your home. And then it may be copper or Wi-Fi combination also. Now, if you see, this is how the fiber is originating from central office and up to what extent it is reaching, it is penetrating into the city, or how it is reaching you directly to your desk. It is shown here. So FTTN, it is FT fiber to the node. It means that maybe the fiber is coming to your outer area in, let's say you live in a big colony or something, and then outside that fiber is coming up to this point. After that, from that fiber, you are either using maybe copper, or then of course you are using Wi-Fi also. So that you can call it as FTTN, that is fiber to the node. If it is coming more near to your house, maybe some 100 houses are there, and then there is a common fiber drop there. So then you can call it as FTTS, that is fiber to the street. Then FTTC, fiber to the curb. They have almost similar meaning. So fiber to the curb, fiber to the building. I mean, let us say you have a big building, and let's say there are 50 houses. So we can say that the fiber is coming to the building, and from there fiber end, from the drop box or from the connection box, you are taking a this copper connection into the houses, and then Wi-Fi also. This is actually fiber to the home, and this is fiber to the desk. So I'm not sure if you people, many of you must be using this fiber to the home now. That fiber is coming to your house, and from there, then you have the Wi-Fi. There is no actually copper now. So I'm sure many of you, this Geo and Airtel and Tata Sky, they are providing fiber to the home. From there, they put a small box which is called ONU, and then from there you can get the Wi-Fi signal into your house. Fiber to the desk, I think it is. It will take some time, right? You can just plug in the fiber into your device. Devices are also not that much compatible right now, but this is giving us sufficient good speed. So FTTX, basically, as I said, X can be anything. It can be fiber to the node, fiber to the exchange, fiber to the cabinet. There are many terms coined, and sometimes they are confusing also, that what is the difference. But there is no real such hard definition or hard bifurcation between these: fiber to the premise, fiber to the office, fiber to the mobile or mass, fiber to the Wi-Fi. There are many terms, but as I said, this one is the most commonly used term: fiber to the home. It means fiber is coming directly to your home now. Okay, let's now move on to gigabit passive optical network. Basically, it is passive optical network, which is called PON. And then if you put a G before that, gigabit passive optical network, it becomes GPON. So now see, this is the general broad, you can say, configuration of a GPON or PON network, passive optical network. First of all, I will tell you why it is called passive network. But before that, let me tell you, there is just one second. There is a OLT here, that is optical line terminal. Okay, so that is at the central office or head exchange central office. So that is connected here at OLT. These are ONTs, that is optical networking terminal, or sometimes it's also called ONU, optical networking unit. These are basically the customers or you people, the premises, fiber to the home. So now you see that there is a single fiber which is carrying data, huge amount of data from here to here. And this is the distribution hub, fiber distribution hub. And then there are splitters here. This is a splitter, this is a splitter, this is a splitter. So what this splitter does, whatever signal is carried from here up to here, splitter, it splits the signal into maybe 1:32 or maybe 1:64 or maybe 128 or so on. So that signal is divided and then each household receives some part of that data. So this is the basic configuration of a passive optical network. Now why it is called passive and why it is so important? It is called passive because in between this OLT and ONU, you separate this ONU and OLT part, maybe this also you can separate. All this portion is passive. There is no active component here. It is all passive. It's all passive. And passive means there is no active component. Active component, you may say it is an EDFA or amplifier or something like that. But passive components, they do not need any power. All these splitters, they are all passive devices. So what is the beauty of this arrangement is that passive devices are very cheap to operate. They are very economical, very easy to operate. They don't need much maintenance. They are cost effective. So from here to here, this complete network, you call this as ODN, that is optical distribution network. It is all passive. And this range is around 20 kilometers. From here to here, around 20 kilometers. So basically, this GPON has actually given PON or GPON has given an opportunity to have a very low cost network with very high data bit rate, which is the characteristics of the fiber. So that is why it is called passive optical network, and gigabit means it is working in gigabit range. So you can, it's a variant of PON, but it is very popular. So it is called GPON. So only passive optical components in the access network. Active components are only installed in the central office, that is OLT on that side, transmitter side, and on the customer provides, because you need a power to power on your ONU. So between ONT or ONU, sometimes I call it ONT, sometimes I call it ONU. So don't confuse, they are almost the same. Only thing is in some standards they are called ONU, and some standards, because you have two standards, IEEE and ITA, but otherwise more or less they are same. So it's only the passive optical network comprising of fiber links, splitters, and connectors. So that is why it is very economical to run and to maintain. So what are the benefits of using GPON technology? It provides very high bandwidth capacity to the user because one fiber is directly coming to your home. Of course, it is through splitters. So splitters, they further divide your speed, but still you get a very high speed. All this 100 Mbps speed which you are getting at your home, Reliance Jio or Airtel, they are actually using this technology now. They provide long reach without amplification. As I mentioned, around 20 kilometers you can easily cover by this technology. They have long physical and economic lifetime, fast and quick deployment. So, I mean, you might have seen that they come to your house for installation, and within maybe half an hour, they can install this. And it supports multiple advanced services for revenue growth. You have triple play services, data, TV, and internet, everything, voice, everything on one fiber. Has no active electronics in optical signal processing equipment. Again, as I said, only in the ODN. But on both sides, on ODN, at OLT and ONU, you need to have active components. Upgrade is also very important and very easy. Now, going further into details of working principle of GPON network. So as I already mentioned, there is a OLT on the transmitter side, and then there is ONUs. ONUs are, it can be n number of ONUs. And then you have a splitter here, which can split to any number of, there are standard splitters available in the market. So downstream is something which is used to communicate from this master, which is OLT, to the ONUs. You call that as downstream, and that wavelength is usually in this range, 1480 to 1500 nanometers. And when the ONU wants to communicate with OLT, then you call it as an upstream transmission. So it's usually in this range. So you can see that you have different wavelengths are adopted in the upstream and downstream direction for transmitting of data. Now, downstream communication principle, what downstream and upstream communication is taking place. Usually this, when the OLT wants to communicate with the ONUs, normally it does in a broadcast fashion. It broadcasts the data to every ONU. Then there are some specific filters installed here which can actually filter out that portion which is meant for this, because they are given control by giving some ID, a location ID. So they can filter out that data which is relevant to them. You can see that this composite signal which is going through splitter, it is split into three parts. But here only one which is meant for this ONU as per the packet information, that is filtered out, and it is received by this, 2 is received by this, 3 is received by this. So main features is it supports point multicast transmission, broadcast the same data to all ONUs and differentiates ONU by JM port ID. There is a specific ID given to each ONU. So there is a filter, and that can actually filter out that data. So now there is something called TDM PON and WDM PON. Now these two concepts are very important and very interesting also. So TDM is nothing but, as you all know, time division multiplexing, and WDM is W is for wavelength, that is lambda, division multiplexing. So in this case, in the top diagram, you can see that this time division TDM scheme is mentioned here. How TDM works here? You see that this is the OLT. There is a data to be transmitted that is modulated, and then there is a transmitter, and then there is a circulator. So circulator actually allows the signal to go only in cyclic fashion. So any data which is coming from here, it will not come directly here, it will go like this. And any data which is coming from this side, it will not go here, but it will always go like this. And any data coming from here, it will go like this. So it is a cyclic fashion. Circulator, this arrow means that you whenever any signal is coming, it will always go here. Any signal coming from here, it will go here, and any signal coming from here, it will go to this. So it works in a cyclic fashion. Any data which is coming from here, it cannot go directly to this. That is the property of this um, circulator. Now you see that this downstream data, it is on a particular wavelength, let us say lambda d, and it is transmitted in a time division multiplexing fashion. You see, if you have 1, 2, 3, 4, 5, 6, let us say n number of these signals, and n number of these signals, just give me one moment. Just one minute. Yeah, sorry about that. So you see that this message is actually going in the time division multiplexing fashion. It means that one particular time slot is allotted to each of this signal. So in one time slot, this first signal is sent in the second time slot. So and as I told earlier that it is splitted in all the users, and then that particular ONU which is tuned to this, it will receive that signal 1 or n. Now, what happens on the downstream direction, or basically what happens in this WDM? This is what is happening here. In WDM, again, you have a number of receivers at the transmitters on the central office, or OLT, you can say. You can also call this as OLT. And all these signals which are having different wavelengths now, not single wavelength just like this, they are having lambda 1, lambda 2, and lambda n. N number of signals, these are actually now multiplexed by using another device which is called AAWG. So one device I told you, it is a splitter which is used to split. AWG is arrayed waveguide grating. So this device is actually acting as a multiplexer and demultiplexer also on the receiver side. When you have a number of wavelengths called n wavelengths, and these are multiplex, and you see that all these wavelengths are now together mixed in time. In time domain they are mixed, but in frequency domain or in wavelength domain they are all separate entities. So they all together pass through this together through this fiber, and then when they reach at this receiver, they are demultiplexed by using another AWG, which is marked as AWG2 here, AWG1 here. So, and then they go to individual. So now here each ONU is actually having a different wavelength. So that is nothing but the concept of wavelength division multiplexing, whereas this was the concept of time division multiplexing. You can have a hybrid system also, hybrid TDM plus WDM PON. That is a advancement of this PON to get even higher higher capacities and higher bandwidth and more number of users. What happens in this hybrid PON, that is TDM plus WDM, you have an OLT here, and this is the optical fiber. Now there is a AWG router here, which I mentioned, arrayed waveguide grating. This is written here. And you see that it divides this into different wavelengths. Lambda D1 is here, D is for downstream, lambda D2 is here, lambda Dn is here, and then this is the WDM part. Here what happens, each of these wavelengths which have been separated by AWG into different parts, each of them is further subdivided into by using a splitter. This is a passive power splitter and combiner. So that splitter that we use, so that is used normally in TDM. So this you can see that if there are n wavelengths here, lambda 1 to lambda n, and then there are, it is splitting it into m parts. So, and here it is, each splitter is having say p number of users. So you will have that your capacity is multiplied m times p, and then also so many wavelengths are there. So this is the hybrid TDM WDM combination of PON. So that gives you even higher speeds. Now, what is a power splitter? Basically, just to give you an idea that how it looks like, power splitter, as I said, it is a passive device, and usually, normally it is used in TDM, time division multiplexing PON. So it's something like this. You have, see, one input here, and when it goes out, you can have a number of output. So this power is basically split into a number of output ports. So that is how the power splitter looks like. Similarly, for WDM PON, as I mentioned, the AWG is a very important device. And that AWG is something like this. So it works on a principle which is something like this, that this actually consists of an array of waveguides. You see this is a one waveguide, second, third, fourth, fifth, sixth, so n number of such waveguides, and that's why it is called an array of waveguides. It's an array of waveguides, and the property of this arrayed waveguide is that each waveguide has slightly different length. Say if I say the length of this waveguide, this is waveguide or fiber, it can be anything. So if I say the length of this is L, then the next fiber or next waveguide would be L plus delta L. The third would be L plus twice delta L, and so on. So there is a delta L difference in the length of each. So what actually it gives you is that if you have an input spectrum at the input of this AWG, now as you can see, input spectrum is having a large wavelength content, all colors, they are represented by colors. It means you have lot of wavelengths. Let us say lambda 1 to lambda n. So because of this property of this delta L difference, there is a phase change in each of the wavelength. Let us say lambda 1 wavelength is there, so it will be passing through all these waveguides. So this length delta L is chosen in such a way. So this length is chosen in such a way that when
Please, participants, please. Yeah. Hello. Participants, please turn off your mic.
Okay. So this delta L is actually designed in such a way that when lambda 1 wavelength, it travels through all these waveguides and reaches here, when it combines back, there is a phase shift. And because of that phase shift from all these components, it will be focused only at a particular point, let us say at this point. So here this fiber actually is collecting lambda 1. Similarly, if lambda 2 is there, lambda 2 is passing through all these, and it will, because lambda 2 is slightly different than lambda 1, so for the same path length of delta L, it will have a slightly different phase shift when it reaches here. So instead of this point, it will focus, let us say, at this point. So there is a fiber to collect this wavelength. So all these wavelengths which were together here, combined here, they will now be separated here. So that is the principle of AWG, and the reverse also applies. If you have lambda 1, lambda 2, lambda 3 from input from here, and when they reach here, they will get a multiplex signal of all the wavelengths combined. So these are the two very important elements and basic elements as far as the operation of GPON, splitting, multiplexing, and demultiplexing is concerned. This is in TDM, this is in WDM PON. And when you have a combination, as shown on my last slide, you have both. This is your AWG and this is your power splitter. Now, historically, if you see historically, then there are many variants of PON. The first one to be developed was APON, that was ATM PON. It was the first passive optical network standard, primarily for business applications. Then BPON was there. I think again there is some noise from some participant. Okay, so this APON and BPON, these were very initial standards, and now today they are not used. They have become obsolete. Then another important development was Ethernet PON, EPON. That actually, and this GPON, they both are quite important standards. The difference, major difference between these two, I mean, they are similar in nature, but the major difference is that this is as per the IEEE standard. IEEE, you know, it's Institution of Electronics and Electrical Engineers. It's a very well-known body. And then this GPON is actually based on ITU standard. So both of these, I mean, they started together. They are still going on, and I think GPON is more common, more popular nowadays. Both of them, they were based on TDM, that is time division multiplexing. So this is just a comparison of BPON, which I mentioned it's now absolute. EPON and GPON, they are still being used. The standard here is IEEE 803.2AH, whereas this is G.984. If you remember in the morning lecture, I told you that there is a standard G.984, which is the system that this standard. So here the bandwidth and all that is also given. So this in this GPON, the downstream bandwidth is 2.5 gigabit per second. Upstream is 1.25. Actually, it is slightly different. You can see not exactly 2.5, but very commonly it is called 2.5, and this 1.244 is called 1.25. So downstream is this, upstream is this. These are some typical applications of GPON, ONT, basically, optical network terminal, or ONU. Just an example I have shown. You can see, I mean, those who are using fiber to the home, they can very well see that.
Excuse me, sir.
Yeah.
Sir, actually, you are the host, so I think you can.
Okay.
Yes, control
But
this.
actually, that my screen is showing PPT right now. Let me see.
Vyangana Gandhi, I think its mic is on.
Okay, I'll try now. Okay, I'll
Yes.
see. Yeah. So this ONU actually is, you can see the typical applications you might have be using this in your homes. That you can have a connection to set-top box, or you can have a connection to PC, or you can have a connection to telephone. Or nowadays, instead of this, this is more common, which is having a Wi-Fi connectivity. You have a Wi-Fi connectivity here. So Wi-Fi, basically, you don't need to put any copper cable just like this, and from the ONT or ONU, whatever you want to call, you can get signal to all your devices, whether it is telephone or PC or TV TV, you have a small set-top box connected to it, which is again Wi-Fi enabled. So that Wi-Fi signal is received from here. Telephone also, I mean, you can have is on mobiles also that they have an application, and that application can be used to access the ONU, and then you can dial the numbers directly from your mobile. And PC, of course, is wireless. So these are GPON standards. ITU dot 984. Basically, this is the common standard, and then you have dot 1, dot 2, dot 3, and dot 4. So these are basically covering the different aspects of GPON network, parameter description, and then specification of ODN parameters. And then, you know, there are various levels. So these are different standards, but mainly I would like to say that this is the standard which is defining the GPON. Now you also have, when you see the connections in PON, there are also methods or ways of protection or redundancy, what you call, because sometimes you have to make an arrangement that if there is some problem or some cut in the fiber due to any reason, then you may transfer your data or load from one working fiber to the another working fiber. Say, for example, you have source, traffic source 1, 2, 3, and this is destination. So if this is the working fiber, this fiber is, let us say it is maybe 50 kilometers. So, but you have to make an arrangement that if this fiber is broken due to some reason, or maybe there is some damage or problem, then because you have a large user base here which can be affected by this, so you would keep an alternative arrangement that it is routed through a different switch. There is a switch and it switches the data from this switch becomes on. Earlier it was off, and then you have a protection fiber here, and that switch, and then that data can be it can be routed to the desired direction. So major traffic sources, they have all this protection fiber. I mean, 1 is to n protection, because n number of fibers, they are using a single fiber as a protection. It's rarely used, but still sometimes it is required if you break the fiber due to some reason. So that is the idea which is shown here. Now there is something called transmission containers, traffic containers, or TCON, which is commonly called. They carry traffic flow and connections and are used for management of upstream bandwidth allocation in the GPON. Because you know that there is a OLT in the GPON, and then you have ONUs on this side. So there is this OLT acts as a master, and it controls all the bandwidth allocation and everything, the time slot given to this, or maybe dynamic bandwidth allocation. So T containers or traffic containers, they are used in GPON protocol. Okay, this is a group of logical connections and treated as a single entity. So TCONs are primarily used to improve the upstream bandwidth, and they enable quality of service implementation in upstream direction. There are 5 TCON types: type 1, type 2, type 3, type 4, and type 5. I am not going into details, just to give you an idea that based on the service level agreement, you know, SLA, there is something called service level agreement. TCONT 1, if this is implemented, it guarantees fixed bandwidth allocation for time sensitive applications. TCONT guarantees fixed bandwidth allocation, but not for time sensitive application. This is a mix of minimum guaranteed bandwidth plus additional non-guaranteed. So basically, this moves from a very stringent or very rigid requirement to relaxed requirement, depending on the type of network. This is TCON 4 is best effort, dynamically allocated without any guaranteed. So it doesn't provide you any guaranteed bandwidth, But it says it will make its best effort to provide you whatever bandwidth you need. And then TCON 5 is a mix of all service categories. Now I mentioned something like dynamic bandwidth allocation. So because you know that one OLT is there and it is controlling many ONUs on this side. So sometimes because if you allocate fixed time slots to each of these or fixed wavelength to each of these ONUs, most of the time it is seen that they are not transmitting anything, and that time or that bandwidth is wasted. Only sometimes they transmit, because normally it is the downstream which is dominant. Upstream is very small and very rare. So this dynamic bandwidth allocation is a scheme in which this OLT can dynamically allocate bandwidth to different ONUs, so that it will result in overall saving of bandwidth. So depending on which ONU is sending a request and which ONU wants to send a data at that time, so dynamic bandwidth allocation can be done. So that will save you energy also and bandwidth also. So this is actually how it is done, and OLT sends data to this, and then there is a request from this, and then request of transmission, how handshaking is taking place. So all that is done in dynamic bandwidth allocation. So OLT is responsible for allocating upstream bandwidth to all ONUs. So there are basically different mechanisms there, and then this is called ranging, which measures delay and sets a register for each ONU. And then DBA, that is dynamic bandwidth allocation, allows upstream time slot to shrink and grow based on the demand by ONUs. It can make them available or not available, and that is identified by alloc ID. Each ONU is given a ID that is a unique ID that is used to identify that ONU. It is just like a packet concept, that you have a header in a packet, and then that packet knows that where I am heading depending on that header. So that is the principle of dynamic bandwidth allocation. Now there is something called GEM, which is GPON encapsulation method. That is full form of this. G is for GPON encapsulation method. So which encapsulates the data over GPON. Although any type of data can be encapsulated, actual data types depend on service situation. So each this ONU has a GEM port ID. This GEM port ID is there on the next slide. You can see this is a ONU or ONT, and then each ONU or ONT must have at least one TCON. It may be more than that. And then you have GEM ports here. So you may have multiple GEM ports also in a given ONT. So that is the relation between the TCON and GEM ports. Now, this is just to show you the downstream GPON frame format, because all data is transmitted in the form of frames. So I am not going into details, but you can see here that this is the downstream GPON frame. This is how one frame looks like. It is 125 microsecond, and then there is a payload here, which is the actual data which you want to transmit. And then on this side, you have some actual information which is used to control or monitor monitoring information. So this is your actual payload, and this complete duration is 125 microseconds. Similarly, you have upstream GPON frame. So this also has some set configuration. You have payloads, and then you have some more data, which is control and maintenance data or some other information. Okay, now coming on to some recent advancements in GPON. Till now, we have studied the GPON. And what is GPON? GPON has become a very common term. GPON is, it means you are talking of 1 Gbps, 1 gigabit per second. If you remember in the downstream, we mentioned that GigaPON has a download speed of 1 Gbps maximum. So that's why it was called GPON. PON is just a general term, which is passive optical network. Now, some of the recent advances which have taken place in GPON is, first of all, is XGPON. Sometimes it is also called 10GPON, or in some books you will find 10G GPON. Various names are given to X. X actually is for 10, the Roman numeral 10. So this XGPON is the next advancement of GPON. Here your data bit rate was only 1 Gbps. Here it has reached up to 10 Gbps down and 2.5 Gbps up. So that is actually ITU standard 0.987, and this was rolled out in 2009. I mean, it doesn't mean that in 2009 it has become 11-year-old now. It is still developing. This was the first time the standard was laid down for using of XGPON. Still, we are far from, in practical reality, we are far from XGPON. We are still using this GPON. Then the next or the parallel development you can say was XGS-PON. It is again, you can say, a variant of this XGPON. The data rate is 10G, but it is now symmetrical. You have 10G up and 10G download stream. So it is again the same standard. The 0 is there. In 2016, it rolled out. And the most popular one, which I am going to discuss in more detail, is NG-PON. That is, NG is for next generation PON. So here you can see that you are talking of much higher speeds, 10G up and 10G down, but there are some more differences also, which I will discuss in the next slide. So actually, this is just a description of what I have already covered. XGPON was there, XGS. It is higher bandwidth symmetrical version of GPON. Same capabilities as GPON, and we can coexist on the same fiber with GPON. This also I will tell you with the help of a diagram later on. So next generation PON actually is a general term. Next generation means it can go up to 100 gig also, or even 40 gig is very common nowadays. So now see, this is the optical network spectrum including NG-PON 2. So ITU-T standard for GPON. You can see here see, this is GPON. So and this is wavelength on this side, on this axis it is the wavelength. So GPON, you can see the downstream was 2.5 Gbps, upstream was 1.5, and the range of wavelengths which were used by this. Dr. Amit, I cannot mute, I just tried. But, I can make her a presenter, that option is there. So if she wants, I can make her a presenter. Anyway, let's continue. So this was, I mean, GPON, normal GPON, 1.25G and 2.5G, and these were the range of upstream and downstream. Then there was XGS-PON, XG-PON and XGS-PON, that is symmetrical. So the important thing or beauty of this is that you see that there is no overlapping of bands of XG-PON with GPON. So when people moved from GPON to XG-PON, this problem was not there that you had to choose any one of these. You can still on the same fiber network, you can use GPON as well as XG-PON, and then NG-PON 2, which I mentioned. So basically, what is the difference between XGS PON, because it is 10 gig symmetrical, and if you see this NG PON, you see it can go up to 10 gig 4 times. So 4 wavelengths are used in this. So effectively, you can go up to 40 Gbps, which is a very high speed, very huge speed that is available. This arrow shows upstream and this shows downstream. And then very importantly, I'm not sure how many of you know that what is an OTDR. Actually, OTDR is it's a very useful device used in optical networks. And I will tell you very briefly here that suppose you have a long network of optical fibers, and let's say this is 100 kilometers long network, okay, and then suddenly, and this is underground, it is buried in ground. So, and then there is a break here. Then how do you know actually that which point is the break? You have to dig out this whole 100 kilometers, which is not possible. So this OTDR actually, it is a very short, small device, handheld device, OTDR. So it is called optical time domain reflector. It is just like a radar for RF. So if you send a pulse, very high intensity pulse from here, then that pulse travels, and then it sees a discontinuity here where there is a breakage. So that will give a big reflection, and that reflection is it is caught by this OTDR because it has a transmitter as well as receiver. So by calculating that time, that how much time it takes to return, you can exactly pinpoint where is the location of the defect or where is the breakage. So that OTDR is actually very important instrument in any optical networks and any laboratories which are doing research on optical networks. So this OTDR band is usually in this range because it transmits one frequency and then that frequency is reflected if there is anything. So this NG-PON, XG-PON, all these, they do not interfere with each other and not even with OTDR. They have a different wavelength range. So that is the important point in development of these. And on the bottom part of this, you can see that GPON, this is all ITU, and IEEE was EPON, and then it has a variation in GEPON, that is Gigabit Ethernet Passive Optical Network. NG-EPON also, they are coming up, IEEE, they are working separately and they are working separately. So this is the development that has taken place in GPON 1. Now this actually XGPON, which I mentioned earlier, that is 10 gig, it is sometimes called NGPON 1. Because what we are discussing here, if you see the heading of this, we are discussing NGPON 2. So XGPON, which I mentioned having 10 gig bandwidth, it is sometimes called NG-PON because you can call anything next generation PON. So NG-PON 1, whereas NG-PON 2 is 40 gig, that is 4 times into 10 gig. So that is NG-PON 2. Okay, now let us come to this point that when GPON was working very fine, you are all getting good speed, 100 Mbps at your home. Why there is a need of GPON? Why should we go to other XPON, XGPON or NGPON? Because I mean, this is a fact that majority of network operators, they have invested heavily in GPON and GPON, which are equivalent architectures, and they are providing services. They are providing you ONUs, ONTs, and fiber to the home. However, since they have been installed, predicted bandwidth needs have increased dramatically, meaning that they now need to change. In the morning, I told you that the hunger of humankind for more bandwidth is never going to end. So that has increased significantly, and then now people have started to find that even GPON is actually not sufficient to cater to the needs of high bandwidth. Mainly because the number of users have increased. You see this OLT is there and then optical splitter. The number of users has increased so much that each user gets a very small portion of 1 Gbps. Maybe you can get 50 Mbps or whatever. So there is a need to change now. So at the moment, the problem with I would not say problem, but the limitation with GPON is it provides 2.5 Gbps down and 1.25 Gbps upstream capacity, which in itself is a very huge capacity. But the problem is, as soon as you share that using a splitter to, let us say, 32 or 64 users, okay, even a very simple mathematics will show you that even with dynamic bandwidth allocation or whatever you try, each user cannot get more than 100 Mbps service at the most. So that is why the problem is there, that soon you will need more bandwidth than 100 Mbps. You want to get 1 Gbps. So that is why this 10 GPON, XGPON, this is XGPON, all these are developments are taking place. And as I mentioned, 10 GPON, or you can call it as XGPON, they can coexist with GPON in the same ODN. This optical distribution network, which is there, this is the optical distribution network. So you can have a GPON also. I mean, this is from this way actually. OLTs are here on this side, and GPON ONUs are on this side. So what I mean to say is that this development which has taken place in XGPON or even NGPON, the good thing is that you do not need to change your this network completely. This same network, same ODN can still use. Of course, you need to change your ONUs, which is just a small device. So NGPON dead end, NGPON 1. Again, remember NGPON is XGPON, or you call it as NGPON 1. So what is the dead end? It delivered performance that was at least 4 times better than GPON, but it provided for 10 Gbps downstream and a range of upstream speeds, including possibility of 10 Gbps. Now, this actually tells you that when GPON was there, already there, so it was providing a speed of 2.5 Gbps. Then came NGPON 1, NGPON 1 or XGPON, which was actually providing you a speed of 10 Gbps. But you need to change the ONU. So the problem here is that just because the network vendors or operators which are there, they did not want willingly to go from here to here, because just for an increase of maybe 10 more users or something like that, they have to change the equipment completely. So this NGPON 1 met a dead end, that is, it did not pick up very well, because NGPON was not much successful, as it required operators to buy completely new equipment for only a 4-fold ultimate capacity benefit. So like GPON, it relied on TDM, and TDM ultimately has a limit, because time division multiplexing, you cannot pack more signals with very small separation, because ultimately somewhere electronics is involved and it has got its own limitation. So that NGPON 1 dead end was there. So directly people or vendors, they moved from GPON to NGPON 2 directly. You might recall, do you remember that if I talk of computers, there were CDs and DVDs were used earlier, CDs and DVDs. Then there was a Blu-ray, and then there was USB stick. So I hope you all agree with me that Blu-ray, which came in between, that never picked up. I mean, it was there that it is an announcement of CDs and DVDs, the Blu-ray, but Blu-ray never picked up. Directly, people went to USB and all that, because when USBs came, that Blu-ray, that the craze was finished. So that's same happened here, similar thing. That's why I gave that example, that from GPON to XGPON to this, directly bypassing this, not much interest shown here, but people now directly move to, because here you have a real big increase in the available bandwidth. So NG.2 solution is actually it's very simple. Essentially, it involves stacking multiple NG.1 systems on a fiber network using time and wavelength division. So as I mentioned, it is using a hybrid of TDM and WDM, and that's why it is also called TWDM technology. TWDM means time and wavelength division multiplexing. This is a name given to NG.2. So that's why at the bottom you can see it is given. So how this WDM and the time division is used in NG.2? Wavelength division multiplexing is provided in the downstream direction, and because you have 4 lasers, OLT lasers with a wavelength multiplexer, and the light is then filtered at each ONU, as I told you earlier. In the upstream direction, tunable lasers at each ONU are assigned a wavelength. Say at ONU is there, and then if it wants to transmit in the upstream direction, then it has a tunable laser, tunable source, not a fixed source, but tunable source. So fibers from all ONG are combined using a passive multiplexer splitter that is time division multiplexing. So here you are using a AWG and here you are using a splitter. So that's the combination of this TDM and WDM that you are using. And this is just an example of NG.2, how I mentioned to you that TDM and WDM are combined in this. This is OLT on this side. Okay, so you have OLTs which are NG.2 OLTs. Then you have a multiplexer here, and then you can see that single in the upstream. This arrow shows this is downstream actually from OLT to ONU. This is downstream. This is upstream from ONUs to OLT. So in the downstream, you can see that you are using TDM. I mean, 4 wavelengths are multiplexed in this AWG. That is the wavelength division multiplexing. But after that, you are assigning different time slots to different wavelengths. And then on the this side, you are using time division multiplexing. So this is just a tabular comparison of GPON, XGPON1, and XGS. This is a typo here, XGS, symmetrical PON, and then NG.2, that is TWDM PON. So you can see the download and upstream wavelengths here. This is, as I said, you call it at 2.5, and this is 1.25 approximately GPON. Then this XG is actually giving you 10 Gbps. This is also 2.5 here and 10 here for symmetrical. Here it is giving you 4 times of that. Here also it is giving you 4 times of, almost 4 times, so 40 Gbps. 40 Gbps. So that's why I mentioned that from GPON, people or the researchers or even the companies, manufacturers, they were reluctant to move to either this or to this because they had only 3-4 times increase, but they had to change all the equipment. But here now they have, if they jump directly from here to here, they have much more incentive, that is in the form of bandwidth. You can get instead of 2.5 you are getting 40 Gbps, so that's a significant increase. So now people I mean this NG.2 should be a reality. So this I already mentioned. All NG.2 can provide up to 40 Gbps throughput to the entire optical network. Of course, 40 Gbps is further with the help of a splitter. I mean, it can be divided, and then the user will not get 40 Gbps directly. One user, it will be divided. But even if you divide it into, let's say, how many 40 users, each user gets 1 Gbps, which is a very huge bandwidth available to you. So that is about this. And as I mentioned here, that because they are using different frequency bands, GPON, XGS PON, NG-PON, they are all actually they designed it deliberately when the researchers were trying to find out a new standard, new protocol. They deliberately left these wavelengths not to overlap this because they wanted backward compatibility also. That if you design a new system, then all GPON equipment should also be able to properly work, provided they have the proper ONU. So that is called the overlay. So you have PON system coexistence here, that you have GPON, RF over ONT, XGS PON, NG PON 2. They are all actually working on the single mode fiber, the same fiber, which is going up to 20 kilometers. So I'm coming towards the end of this presentation now. So what is the future of GPON? Because we have seen that maybe from 2010 or before that, let us say in 2000, you had the GPON. Then you had XGPON 1, then NGPON 2. So what is going to happen next in 2020? We are already there. What is going to happen next? So we are already, I mean, here where we are using hybrid systems, TWDM and TDM and WDM. Reach, you can say easily we can go up to 100 kilometers. But what is going to be next is that obviously they will have more convergence. You will have downstream of 100 Gbps, upstream of 10 Gbps. This is just a prediction. I exactly cannot say that this will happen. Maybe more happens or maybe less happens, but this is just a prediction I'm making based on the researches and data available. So more than 10 Gbps downstream per user, it will be available. Okay. Reach will be much more than 100 kilometers. The split ratio of splitters, it will be because there are developments in this technology also. The splitters are even getting more and more lossless and low loss. So 1024 splitters also you may have. You may see this in real. So future of GPON, continuing with that, I mean, again a prediction up to 2025, you can see that the downstream rates and the upstream rates, they are, this is the average downstream bandwidth, and this is the average upstream bandwidth. So bits per bit rate per subscriber, you can see right now we are somewhere here. So we are almost there, 100 Mbps is we are getting. Maybe not in our part of the world, but people might be getting 100 Mbps. I think here also 100 Mbps it's now becoming very common. Reliance and Jio, all that, they are giving 100 Mbps. But later on, we can expect even more developments in this, and I mean, can expect more speed, 10 Gbps or maybe even 100 Gbps. May not be very far when you have this bandwidth. So that's all about this GPON, and I know that there are some more lectures scheduled on this actually in the later part. How to do the switching, how to increase the energy efficiency, what are the various other issues which will be dealt in detail by other experts in this course, short-term course. So I just wanted to give you an overview of GPON, what is GPON, and APON, DPON. Of course, I told you that these are now obsolete, but GPON and GPON, that is, these are two different standards. This is ITU and this is IEEE. And then further you have XGPON, and your NG.2, which is very important now, which is a combination of PDM and WD. Yeah, so that's all from my side for this lecture. Thank you.
Thank you, sir, again for giving very informative lecture on GPON. You have given us various ideas about the GPON, various kinds of passive optical networks. So thank you, sir. Participants, please.
Hello. Hello, good evening, sir.
Yeah, good evening. I just, yeah, tell me.
Sir, can we apply TWDM concept to EPON?
EPON, yes, why not? I mean, these are two parallel standards. You are using, I mean, this is by ITU and EPON is by IEEE. But there is, I don't think there is anything which can stop applying that concept there also.
Yes, sir. Thank you, sir. Sir, can you elaborate the works related to FTTD? I think you told
FTTD.
It will be.
What do you mean, FTTD?
Desk, sir. Fiber to the
Fiber
desk.
to the desk. Yeah, I mean, right now, I don't think that it has much penetrated into up to the user. Right now, you are only having FTTH. That is, you have a ONU at the house, and then you use Wi-Fi or copper cable or LAN cable. But fiber to the desk, actually, it will take more time because your devices also need to change in that. Say you are using a laptop, and right now, what type of connection you have? You have either a LAN connection or a Wi-Fi connection there. But if you want to use a LAN with fiber, I mean directly fiber connected to your laptop, so maybe it is going to take time. Of course, you will have a huge speed in that case. So maybe I think before that you have a fiber port directly in the laptop. I think you may have some connectors in between. They may evolve that USB fiber to USB connector or fiber to LAN connector or something like that. But true FTTD will be only when your devices are capable of directly handling the optical signal.
Yes, sir. Thank you very much.
Is that all?
Yes, I think there is no question from the participants. Okay, so thank you, sir, for giving such a great informative lecture. Yes, sir, thank you.
Okay, thank you. Thanks.
And there is one more information for the participants. Participants, please, I've sent you one link that is for OptiSystem. So kindly install that software because tomorrow and day after tomorrow you have some lab sessions on that. So please install the software and join at 10 a.m. tomorrow morning for the next session. Okay, thank you all.
Okay, thank you.
Yes.
Thank you very much. Thank you.